Hi, good afternoon. My name is Antonio Ponce Garcia, and today I'm going to present my problem situation, modeling of an active suspension system for an automotive vehicle from my course, Modeling and Automation. For this study case, we had to investigate about an active suspension system. An active suspension system is a system mainly used in cars and vehicles that can help them gain a better control despite the disturbances of the road in order to increase the driving experience. As you can see from this example of an Audi A8, the various mechanical parts from the dampers and suspension system come together to create a better system that we will discuss in more detail as we go on. This activity was done in teams, which means we had to take part in collaborative work. As for the development we had for this, everyone did the equation modeling on their own. This was done so we would not commit common mistakes, and then we had a big discussion on where we went wrong. And once everyone finished their equation modeling, we got together either digitally or in a common space to discuss our results, where we could corroborate our results or discuss which model was the one that we did correctly. And once we were done with this, we jumped to the block system development, which was done in MATLAB and Simulink, where we could digitally generate graphs that could describe our model's behavior. Working in teams and collaborative work usually has its pros and cons. Its pros includes task distribution, so the workload doesn't fall on a single person, brainstorming and idea sharing, which increases the variety of ideas, increased efficiency if the team works appropriately, and result discussion, where we can discuss mistakes or everyone can look after each other. The cons include team disagreements and clashing points of view, which can sometimes alter the team's structure and can slow development of the situation, as well as complicated organization, since everyone has their own schedule and it's difficult to organize a common time. My participation in the collaborative work included mainly research and documentation of the general study case, which is the active suspension system, the modeling of the equations and solutions by paper, as well as organizing the team, which means assigning dates where we could meet up and do this and work in this problem. The scope of the community for this project is to further investigation on suspension systems, as well as the development of diagrams that can describe the system's functionality. We also intend to prove the system functionality using digital simulations in the digital software MATLAB, which includes Simulink. Our research methodology was split into 5 main steps. The observation mainly included the investigation of the case study, in which we studied previous reports and investigations done on active suspension systems. Once we were done writing a report, we jumped to the hypothesis, which included the system analysis, in which we analyzed the system that we found and tried to describe its functionality using block diagrams and other tools. Finally, our experimentation was done using digital simulation. Since we did not have access or way to build a motor ourselves, we did it using the digital software MATLAB that could help us simulate the behavior of our system using graphs, which were our results in which the suspension and car behaved along the road. Finally, our conclusions consisted in going back to our hypothesis in order to see if we were right and writing down the new knowledge that we acquired. It is important to know that there's more than one suspension type. There's the passive suspension, semi-active suspension, and active suspension, each one with their own advantages and disadvantages. The passive suspension has high affordability and is found in many commercial cars. The semi-active suspension includes sensors that control a damper that can add adjustment in the stiffness of the damping force and enhances drive comfort. As for the active suspension, it now comes with an actuator that can generate an extra force that adds superior adjustment capabilities against the road disturbances. Going back to the active suspension mainly works on electromechanical mechanisms that modify the damper's behavior while it's in movement. Here we can see as a diagram of how the active suspension works and the variables it includes. Here we can see it includes an MS, which is the vehicle's mass or sprung mass. MU is the tire axis mass or on sprung mass. KS indicates the spring stiffness. CS, which is the damper located here, is the damping coefficient. FA is the force generated by the actuator, the active control force. KT includes the tire stiffness. CR includes the road excitation. CS and CU are equal to the absolute displacement of the body. And if you subtract them, you get the suspension displacement. And finally, the double derivative of CS and CU gets you the body's acceleration. Here we can see a more simple schematic of how the active suspension system works. As we can see, 2 sensors send signal to a control that then indicates the force actuator, how much force it needs to be put into the sprung mass in order to elevate the vehicle to avoid any road disturbances. In order to gain a better understanding of this model, we needed to use dynamic equations. Here we can see the equations for the active suspension system and passive suspension system based on the model we can see here on the left. As we can see, ms times the double derivative of cs equals to minus ks times the difference between the sprung mass and the unsprung mass, minus c for the difference of the derivatives of the sprung mass and the unsprung mass, plus the force generated by the actuator. Since the passive suspension system does not count with an actuator, it doesn't need it's basically the same equation, but without the final force added. Part of our hypothesis mentioned previously was the description of the system using a block diagram. Here is our proposal of how the system mainly works. Using a reference signal, the system sends a signal that a PID controller or a proportional integral derivative sends, and using a power interface, which based on our course can be op-amps or operational amplifiers, tells the actuator how much force it needs to produce. This force can be generated by a pneumatic or hydraulic ball, and this generates the system dynamic. Based on the result, the system sends a feedback to the position sensor that reads the floor profile and adds it to, subtracts it to the reference signal, which then repeats the process, gaining constant feedback. The equations, here we can see the development of the equation, mainly the transfer functions, which include CS over CR, CU over CR, and C acceleration over CR. Here we can see our base equations and how we cleared and got the single CU and CS, and then we divided them over CR, giving us these equations which were our transfer functions that we would later use in Simulink. As for the state space, here we have the definition of our state variables. We can see CS is equal to the double derivative of CS is equal to the derivative of x2, and the same for all of the other variables. Here we can see that how we got the CS and CU separated and assigned them their corresponding state variables, and how we arrange them in a matrix in order to meet the requirements of the equation x derivative equals to AX plus BU. We did the same for the output variables, and here we can see our results. Once we had the transfer functions, we implemented our results in the digital software Simulink using this block diagram, which included the transfer functions, as well as different muxes and scopes, which allowed us to see the behavior of each individual variable depending on the values we introduce. For example, for the specifications listed here, we have the behavior of the passive suspension CS and the active suspension CS with a force of 200 newtons. We can see here how the graph behaves. The same with CU, CS minus CU, and the acceleration of CS. We also did this for using a sinusoidal input, which allowed us to see the bumps of the road, the behavior the vehicle has in the bumps of the road. Here we can see the same for the CS and active suspension, for the passive and active suspension, CU, CS minus CU, and CS acceleration. Although normally the active suspension system should be more accurate, which means in this case, here we can see the passive suspension system, which is now is below the active suspension one. It should normally be the other way. However, this may be due to the lack of information, since the active suspension system is supposed to be more accurate due to the added force that the actuator generates. In order to gain a better understanding, we had to do a literature review of a previous case study developed made by our teacher along with other specialists. This was about the exogenous input model-based predictive control strategy, which here we can see its basic schematic and functionality, and which this system uses a driver block applied in a semi-active vehicle suspension to reduce the computational load of the closed-loop semi-active suspension. This literature review also helped us gain a better understanding of the different systems. The passive system, in one hand, generates a force directly proportional to the difference between the speed of the suspended and sprung masses, and has a constant proportionality established when the shock absorber was designed. The semi-active system has a damper with a baseline value and can be increased by adding extra stimulus. As for the active system, this changes the damper's characteristic during the operation and has no base value. The literature review also included the equations needed to model the system, as well as the description of its variables such as K0, C0, alpha, CBW, and beta, Y, and S. Here we can see the equations. And finally, here is the block diagram of how the system works, which the driving trajectory is generated by the driver blocks, which we can see here, and its output is a stable model with the desired dynamics. The predicted model is made to calculate the control signal from the desired output generated by the driver block, as we can see here, and this generates us the rendered desired output equal to the system predicted output. My individual contributions to this problem situation included mainly the topic investigations and research about passive, active, and semi-active suspension of a one-fourth of a vehicle. Finally, I was mainly in charge of making the transfer functions and state space modeling. Here are the references that we used during our problem situation, and thank you for your attention.